Welcome to the lecture series in computer science. As a part of this series, we are doing artificial intelligence and we are in unit 3 now. In unit 2 we saw about searches, in unit 3 it is about the reasoning methods, and we started off with proposition logic in the last lecture, and today we will be starting with predicate logic, and this is a continuation of the proposition logic, and in this topic we will be doing these things today, where we will start with the introduction to predicate logic and how it is slightly different from the proposition logic, and the use of quantifiers. The basic difference between the proposition and the predicate is where we are using the quantifiers, and with the help of the English statements and how we are going to translate that to predicate logic, we will see that also, and we will also look at how to convert into CNF, which is conjunctive normal form. You might have done already in the discrete mathematics. A similar problem will be handled here, but with the application in the reasoning methods pertaining to AI, we will be seeing it in this session. Okay. Just an introduction of the predicate logic. It is otherwise called as the first order logic. So, it actually includes all of the proposition logic, and again with the proposition logic, which you would remember as and, or, not, which are the operators, the proposition sites, as well as the implication. And you would also remember that the logical values of the proposition, which is otherwise as a fact, that are evaluated to either true or false. Say for example, today is sunny or today is 36 degrees centigrade, that can be considered as either true or false. Those kind of statements which are the propositions, this is going to be belonging to the predicate logic as such. Then the variables phi or psi, which is again a formula in the proposition logic structure, along with the constant p, q. P is just a fact, a single literal, we call p as a literal. Then the connectives, not, which is the negation, which we saw earlier in the proposition logic. This is the this is and, which is the conjunction, or, which is the disjunction. This arrow which is towards the right, that is called as an implication, and a line with a double arrow on the either side, this is called as an equivalence symbol. The first thing was the proposition logic side. The second is the constants that will be included in the predicate logic. For example, AI, this is a constant. John, the name of the person, is a constant. Number 2 is a constant, and so on. Third is the predicate. This is a major difference between the predicate and the first proposition logic, where for example, in the predicate we would describe something as mother, mother of, sister of, less than or greater than. These symbols or these items are called as the predicates. Another one is a function. Function is the square root or mother of. So, earlier I said mother, it is going to be within the bracket, say x and y. Say x is a mother of y, that is called as a predicate, whereas a function is something very similar to what we use in the programming language, where a function is returning back the value. Like if I say square root, what is square root of 4? The answer is going to be 2. So, returning back that function's answer is the method that we are using in the predicate logic. So, we in the predicate logic we have these 4 items, which is all of the proposition logic. The second is the constants, the third is the predicate, and the fourth is the functions. So, with these we will also have the most importantly the quantifiers. The quantifiers will be the as the name indicates, it is the counting options. So, here we have 2 major quantifiers. One is for all exist, you could see an inverted A here, that is for all or for each. The other one is the inverted E, that is represents there exists symbol. So, with these we will be using that for our predicate reasoning. So, how are we going to use that for the reasoning process? We will be seeing that in this session. So, here the constant, it does not occur alone. Suppose for example, we say Alfred is a boy, and in the predicate logic structure we will say boy within brackets as Alfred. Here you see whatever within the brackets, this is called as a constant, and the boy portion of it, this is called as a predicate. Whereas the function, it is, as I said earlier in the last slide, the functions actually returns back a value. For example, if we give add of within brackets 2 comma 2, it will return back 4. The predicates here, the function is, the predicate will return back the truth value. It will either give true or false, whereas function, it gives the value itself. So, suppose we say Alfred is a boy, that same example that we have taken, with Alfred as a constant and this boy, it is going to be a predicate, and boy of Alfred, we can evaluate it as to true or false. The next is, how will we identify a quantification? How do we apply it? For all is the symbol, an inverted A, it is read as for each or for every. Say for example, here is an example, for all x if x squared greater than 0, which means x squared is greater than or equal to 0. And always remember, this is very important, implication will always go with for exist. An example, every student is bright. If we want to convert this example into a predicate logic structure, then it would be for all x, if x is a student, then he is bright. This is the right correct method of representing an implication with the for all exist, and just the rule of the thumb, if they all exist, then there is an implication symbol here. So, if x is a student, then that student is bright, that is the meaning behind it, or it is called as every student is bright, that representation is given. On the other hand, there exists symbol, this is inverted E, it is read as there exist or sums sum. So, in this case, like we said, for all that we have to use only there implied symbol. Similarly, for there exists symbol, we will be only using and. We should not use there exist with implication or there exist say for all with and. Those two are prohibited, we have to use, and the meaning is also intuitively correct. When we are using for all, it has to go only with the implication, and similarly when we use that exists, it has to go only with and, it will not go the other way around. Say for example, there exists some person whose name is Ram. This is given as, if you see here, there is a student, there exists some student and that student name is Ram. So, this is the representation examples of for all and there exist. And there are some properties of quantifiers which we have to note down while we are translating into predicate logic. Say if you take the first one, for all x, for all y, this is actually equal to the other way around, for all y and for all x. The first one is correct, and similarly the second one, there exists x, there exists y, it is the same as there exists y and there exists x. We can map it to some examples and proceed it. On the other hand, if we write for all x there exists y, it is not going to be the same as there exists y and for all x. This is wrong. And similarly the other way around, there exists x and y is within the scope of x in this case. It is not equivalent to for all y and there exists x. So, whenever you have such kind of things, this kind, we say that y is within the scope of x, and in this case here x is within the scope. See, whenever there exists y within the scope for all, we say y is within x, and similarly here in this case x is within y. It is not the other way around here. Okay. And whenever we have, it is always better to put a Venn diagram for this, which I will show in a few minutes. In this case, this is the third type of property that we have to remember. In this case, f is a function for all x, and there is a function of x that is equivalent to not of existential x negation of f of x. You see here, for all x it can be converted into existential by adding a negation before the quantifier and after the quantifier here. And similarly, if we have to convert the existential quantifier to the universal quantifier, we have to add a negation here. So, this is a very important property that we will be using in our reasoning methods. Now, when we have a Venn diagram for this, it would be representation would be very clear. Suppose we have x and we have y. We call for all x there exists y. We have to remember in terms of there is a whole method of x and within which there is some y. In the other hand, if we have something like for all y there exists x, it would be something like there is a Venn diagram of x and within that space there is some existential. No, this is not correct. This is wrong according to this form. It would be actually for all y there exists some x. This is the correct one. For this is the correct one. So, this slide represents some of the quantifier properties which are very important. Now, we will see a few examples of how to translate the English statements to predicate logic structure. The first one, every house is a physical object. How do we represent that? So, if you see, if x is a house and then x is a physical object with the quantifier of for all x. So, this is a representation of the statement. The second one, some physical objects are houses. Remember, whenever we have some, we have to associate it only with an and symbol. So, if you see, the translation to that will be if there is a physical object x. So, there exists some x and that x is a house. That is a representation of the second term, and every house has an owner. The representation is this owner, an owner can be represented as there exists y and y is an owner. So, there exists y owns x where x is a house, and if you see, every house is represented as for all x. If x is a house, then that house is owned by an owner. That owner is represented as an existential clause, which is y. Everybody owns a house. The difference between here and here, here every house is an owner. In this case, the quantifier, the scope is with all persons, everybody. So, here it is slightly different, where you would have for all x, where x is a person, there exists y, where this y is within the scope of x, y is a house, and given these two conditions, x owns y, x is a person who owns and that person owns y, which is a house, that represents here. So, you could see the difference between the third statement, which is every house is an owner, how we are representing this statement, and everybody owns a house, which is represented using the fourth statement. Now, there are a few more examples here. Some own a house. So, here you see some is also an existential clause. The two items here, the house also is an existential one. So, if x is a human, there exists x and there exists y. If x is a human and if y is a house, then x owns y. You can see the difference between here as well as the previous one, where previous we said everybody, here we have said some. So, here we are not using the implication factor, but we are using only the and clause here. And another example is Sue owns a house. In this case, there exists y. If y is a house, then Sue owns it, and Sue owns it. It is not then as an implication, but again it is an and clause, because there does not have a for all here, and there is implication is not given here. Okay. And Peter does not own a house. So, if you see, there are Peter is a constant, house is a predicate, and a house, it represent the quantifier of there exist. So, the information would be there exists would be Peter does not own a house, where you can write it as house owns Peter y. You can derive from here. Peter does not own, it would be something of the form, and please think about it, how we can represent using there exist also a negation with not owns. Will it be the not negation of it, will it come before there exist, or will it come before for all exist? You think about it, and we will discuss about this in the next class, the representation of Peter does not own. Again, this will be a form of how we derive from Sue owns a house. Now, we will go to the next portion, where we are going to convert into a CNF. So, everywhere that John goes, Peter goes. Consider this statement, where we can say wherever for all x, if John goes to x, there Peter also goes. So, that this statement can be represented here, and John goes to school. So, if you see, go, the same predicate is given here, this go is same predicate here, the same John, which is going to be the constant here, the same constant here, but x being substituted with the school. In the place of x, we have school here. So, please note this point here, where we have the same predicate and the variable of school being substituted with x. Now, how do we convert this into CNF? Now, why do we need to convert into CNF? Like we saw in the last session of the proposition logic, if we are converting into CNF, then the resolution becomes simple. So, here also the same procedure, before getting into the resolution, we have to convert into conjunctive normal form. So, once here, because we have the quantifiers for exist quantifier and for all quantifier and their existential quantifier, because of those, we would have a 9-step process of converting that into a CNF. Now, we will go through the 9 steps of converting a single predicate logic statement into a CNF value. Here, this whatever I am taking, it is taken from Elaine Rich and Kevin Knight. This is a 9-step process, which we are going to convert a predicate logic clause into a conjunctive normal form. So, the first step, and before we start, we will have a same example that is given in the book. and this is a running example, right, where we will throughout the 9 steps we will follow only the same example. Say the example runs like this: all Romans who know Marcus either hate Caesar or think that anyone who hates anyone is crazy. Suppose you take this example. Once we convert that into a predicate logic structure, we have like this, like for all Romans we are representing as for all x if x is a Roman. Who know Marcus, we are representing it as x is a Roman and he knows Marcus. Either hate Caesar, that we are representing as that implied by x hates Caesar, or think that anyone who hates anyone is crazy. So, this portion of it, think that anyone who hates anyone is crazy, is represented with for all y, anyone who hates anyone, it is represented by hate, y hates z, where z, there exists symbol of z, z is within the scope of anyone which is y, and think crazy, where x belongs to the Roman. Roman thinks crazy about y. So, this statement, think that anyone who hates anyone is crazy, is given by the statements. And remember, there are more variations if you and I are able to represent it using a predicate logic structure, but for consistency we are taking the same statement that is available in that textbook. So, this is the example predicate clause that we have right now. Now, what we are going to do is, from this predicate clause, we are going through the 9 steps and derive a CNF out of it. And remember, a CNF is something where the conjunctive outside and the disjunctive within this brackets. So, outside the bracket, so it should be something like A or B and C or D. The conjunctive normal form should be something like this, where the first one belongs to the first conjunct and the second one belongs to the second conjunct. So, we have to bring this formula into this type of clauses, that is our aim. Now, the first step is going to be the eliminate implications. So, whenever we have this, so this is the first clause that we have, this is the predicate formula that we have from the previous slide, the first this point. So, first step is the eliminate implication, and how we are eliminating implication is by looking at, if it is x implies y, we can replace it by not x or y. So, if you see this formula, there are 2 implications here, the implied symbol over here and the implied symbol here. So, if we are replacing it with not x or y, so the first implication symbol, we are adding a not Roman of x and no x Marcus or hate x comma Caesar, and the second implication here, this portion y comma z implied think crazy, that is replaced with or here. So, this is the first step. The second step would be reduce the scope of negation, meaning apply De Morgan's here. Whenever it is not of P, it is P, and not of A and B, it is not A or B. And remember, the last two we looked at the properties of quantifiers. So, when you have the existential quantifier, it will be converted into universal, and when you have the negation of universal quantifier, that will be converted into existential. Now, talking about the previous approach, see, earlier we have this formula. After applying end of step 1, we will have this formula. Now, with this clause, if we apply the negation of it, reducing the scope using this negation, if we push the negation inside using De Morgan's, this would become not Roman or not no. This is a simple De Morgan's. Again, we have a negation symbol here. When we push here, it becomes there exists z will become for all z. That is how we get for all z and not hate y z or think crazy here. So, this is after the result of pushing the negation inside. The third step would be the standardizing variables. This is needed because if we have a number of clauses, when we are doing resolution, this would help because we have only one single predicate formula here, we are not applying this step. Next step is move all quantifiers towards the left, where we would see here we have this is the result of the step 3 outcome, and after step 3 this is the step 4 where we have all the quantifiers for all x, and if you see for all y and for all z appears here after a few clauses. So, this can be moved towards the left, which is after step 3. Step 4, after applying move quantifiers toward the left, y and z goes towards the left, we get this result. Rest everything is the same, not Roman of x, not no, and hate Caesar, hate x comma Caesar, or not hate y z and think crazy will appear the same as the above one, okay, except that the quantifiers y and z moves towards the left. In step 5, we are eliminating existential quantifiers. We are doing it through two ways. One is column constant, another one is column function. Suppose we have something like there exists x p of x, then we will just call it as a constant and we will write it as column as constant. On the other hand, if there exists symbol is going to be within the perspective of for all x, then we would write that y as a function of x. For example, if you see here for all x p of x comma y of x, this y of x is a function of x. In this case, we are going to call it as a column function. In this way, the objective is we are eliminating the existential quantifiers. Why? Because at the end of 5th step, everything will be the universal quantifiers. So, in the running example, because there are only universal quantifiers, we have not eliminated it, and step 5 is not necessary for our example. In step 6, we will just drop the quantifiers because it is no longer necessary. Once we converted into universal, it is not necessary. So, all these quantifiers are just dropped. So, we get this as a result, not Roman of x or not no and until think crazy. In step 7, we are going to have a conjunction of disjuncts, and this we are will be using distributive law if required. So, here if you see this is the result of the previous step, and if you just remove the brackets because this is straightforward, without distributive law itself we are getting this as a result. This becomes we are almost close to the 9th step, we have got this result. And 8th, we need to create a separate of clauses. Suppose we have an and, then we have to break it down into two different clauses. It is not necessary in a running example, like as I said earlier, suppose we have suppose our result has something like A or B and C or D. We will have two different clauses, C1 would be A or B and C2 another clause would be C or D. So, this is the step 8th representation, and step 9 is again we have to standardize apart. Why? Because if we have number of predicate formulas, then we need not have the same variable appearing again and again. Suppose the first statement says x, the second statement also says x, there will be a confusion. So, instead we would just mark it with a subscript like the first statement with x1, the second statement with x2 and so on. So, finally, after the 9th step, this is the result that we get out of it. Here we have not standardized it, but in our next example which we do it in the next session, we will be using the standardization procedure. So, this is about this session where we are closing the session with the introduction to predicate logic, where we saw in addition to the proposition logic, we saw a few terms with the predicate logic, including the main point is the quantifiers, the predicates, the number of arguments that runs inside the predicates, and also the functions. And apart from that, we saw a few examples of the translation to of English statements to predicate logic, and how we convert the predicate logic formula to a CNF, a 9-step process we saw in this session. In the next session, we will see a few examples of converting into CNF and then solving a problem using resolution.